We often think about strong materials for, big things, bridges, buildings.
Huge structures, yeah.
But what happens when you shrink things way, way down? I mean, think about microscopic devices, often made from polysilicon.
MEMS devices, right.
Exactly, MEMS,
Right.
microelectromechanical systems. And these tiny things, they move, they sense on a scale that's almost invisible. Their whole function relies on the material being strong and reliable.
It really does. And when you get down to that microscale, the rules can kind of change. Material properties we take for granted, like fracture toughness, basically how resistant something is to cracking, become absolutely critical.
Especially for MEMS, right? If movement is the point, a tiny crack is game over.
Total failure, yeah. The big question, the puzzle really, is how well do we actually understand polysilicon's fracture toughness at these tiny sizes, especially after it's gone through all the specific manufacturing steps needed to make these MEMS devices?
Okay, so to dig into this microscopic mystery, we've been looking at some fascinating research.
Yeah, a specific paper.
A paper called Fracture Toughness of Polysilicon MEMS Devices, published in Sensors and Actuators, A Physical.
From Elsevier, yeah. The authors are H. Kahn and Tayebi, R. Ballarini, R. Mullen, and A. Heuer. They're all from Case Western Reserve University.
Right. So our mission today is to unpack how they actually measured this crucial property on such a small scale, why it's so important, and what their results tell us about how reliable these miniature machines actually are.
Well, the first thing that jumps out is just how fundamentally difficult it is. How do you even test the strength of something so tiny?
Yeah, like you can't just grab it and pull it apart.
Exactly. Your traditional methods, applying external forces, they just don't work. Trying to physically stress a structure that's only a few micrometers wide, it's like trying to test the strength of a single grain of sand by hand. It's not practical.
Totally impractical. And the paper points out that previous attempts, they had their own problems too.
They did. Some tried using micro-machined notches, sort of pre-cutting a tiny weak spot to encourage a crack to start there.
Okay, makes sense.
But the issue is, these tiny etched notches, they aren't perfectly sharp like a natural crack. They have a slight radius, a curve, at the tip.
Ah, not a true sharp point.
Right. And the calculations engineers use to predict fracture, these stress intensity factors, they assume a perfectly sharp crack tip, a singularity. So using these rounded notches, it introduces errors. It's like trying to measure precisely with a ruler that's a bit bent,
Gotcha. So the measurements weren't quite reflecting the true material property.
And there's more. The process used to etch these notches, it can leave the sidewalls with different levels of smoothness depending on the technique.
Okay.
And that smoothness or roughness can actually influence how the crack behaves. So your results might end up telling you more about your etching method than about the polysilicon's inherent strength.
So artifact of the measurement method itself.
Pretty much. The paper does mention some earlier work, people using external load cells, piezoelectric ones, or even wedge loading techniques on these notched samples. They got some numbers, some critical stress intensity factors, but still that underlying issue of the not quite sharp notch was always there, casting a bit of doubt.
Okay, so given all those headaches with previous methods, what did the Case Western team do differently? This is where it gets really clever, I think.
It really is. They developed this completely novel on-chip testing solution.
On chip, so built right in.
Exactly. Instead of trying to push or pull from the outside, they fabricated their polysilicon test samples, the little beams they wanted to break, right alongside tiny electrostatic motors or actuators, all integrated onto the same silicon chip.
Wow, okay. How do those tiny motors work?
Well, think of them like microscopic combs with interlocking teeth placed incredibly close together. When you apply a voltage between the sets of teeth, they attract each other electrostatically.
Like static electricity, but controlled.
Precisely. It creates a tiny, controllable pulling force. And by designing it so these actuators pull on the end of their test specimen, they could apply the force needed to actually fracture the polysilicon.
Without ever touching it from the outside world.
Exactly. No external loading needed.
That seems like a huge advantage. It immediately gets rid of that fiddly problem of trying to attach a microscopic thing to a macroscopic testing machine.
Huge. Plus, the whole experiment can happen right there on the chip, potentially in a very controlled environment, maybe even inside a scanning electron microscope for observation.
And they mentioned it opens up possibilities for fatigue testing too, right? Like stressing it back and forth really fast.
Yeah, that's a really exciting prospect. High-frequency cyclic loading, that was much, much harder to achieve with the older methods. This on-chip actuation makes it feasible.
Okay, clever actuation. But you still need that starting crack. How did they make a controlled, sharp crack in something so small?
Good question. They use a technique called indentation, specifically with a Vickers indenter,
Vickers, okay, like a tiny pyramid.
a very tiny, very hard diamond pyramid, yeah. They press this into the surface of the polysilicon film. This creates small radial cracks extending outwards from the corners of the indent.
Okay, but pressing something hard like that into a thin film must create a lot of internal stress, right? Wouldn't that mess things up?
Absolutely, and that's where a really crucial step comes in. Annealing. They heated the samples up to 1,000 degrees Celsius.
Wow, really hot. Why?
That high temperature bake is essential to relieve the residual stresses that get locked into the material during that indentation process.
Makes sense. Relax the material.
If they didn't do this annealing step, they saw something called delamination. The polysilicon layer around the indent would actually peel up and detach from the substrate underneath.
Oh, so the whole thing just falls apart.
Pretty much. They show an S image in the paper, a scanning electron microscope picture of what happens without annealing. It's dramatic. The area around the indent is completely lifted and cracked far beyond the intended starting points. It really highlights how much stress that indentation introduces and why the annealing is critical.
That image really drives the point home. Okay, so the indent, then the anneal to relieve the stress. What's next to get those nice, sharp cracks ready for testing?
After the annealing, they did a second etching step. This step was designed to carefully remove the original indent itself and any potentially damaged material right around it.
Cleaning it up.
Exactly. What's left behind are those sharp radial cracks that were formed during indentation, now emanating from a clean edge.
And these are the atomically sharp cracks they mentioned?
Well, they use that term. It's important to realize, at this scale, atomically sharp probably means the crack tip radius is maybe a few atomic spacings across. It's not a theoretical singularity, but it's about as sharp as you can realistically get in a physical material.
Extremely sharp, then. Much better than the etched notches.
Definitely. Oh, and they also cleverly included a microstrain gauge on the chip itself to measure any remaining internal stress in the polysilicon after it was released from the substrate. They found it was pretty low, about 12 megapascals plus or minus 5.
Okay. Now, something else I noticed in the paper was about debris. Leftover photoresist getting stuck in the cracks during fabrication.
Ah, yes. Good catch.
That sounds like you could definitely interfere with the crack growing, couldn't it?
It's a valid concern, and they were aware of it. They even show SM pictures where you can see this debris, which is likely also polysilicon residue, lodged in the cracks.
So did it affect the results?
Their argument is that this debris is mostly loose, not really bonded to the main crack faces. They believe it doesn't significantly impede the opening of the crack or the overall movement of the test structure. So while it's there, they concluded it probably doesn't have a major impact on the final fracture toughness measurements.
Okay, fair enough. It's something they considered. So they've got their on-chip actuator, they've got their sharp annealed crack. How did they actually run the experiment? How did they break the beam?
So first, they had to know the starting point. They used the lathe, again, to very carefully measure the initial length of each sharp crack before testing.
Precision is key here.
Absolutely.
Right.
Then came the actual test. They used DC electrostatic actuation, basically. They slowly ramped up the voltage applied to those comb drive actuator.
Increasing the pulling force.
Exactly. They increased the voltage step by step until snap. Catastrophic crack propagation. The polysilicon beam breaks suddenly.
And they record the voltage right at that breaking point.
Precisely. That critical fracture voltage was the key piece of data from the test itself.
Okay, but how do you get from that voltage to the actual fracture toughness, the KIC value? You need to know the force, right?
That's the next crucial step, and it turned out to be a little bit tricky.
Why is that?
Well, their initial plan was probably to calibrate the actuators, to figure out exactly how much force was generated for a given voltage. But they found this voltage-to-force relationship wasn't perfectly consistent from device to device.
Why not?
They suspect it was likely due to those tiny bits of debris we just talked about. Maybe some particles occasionally getting under the moving parts of the actuator, causing slight friction or unpredictable behavior.
Ah, the microworld strikes again. Even with all this control, there's still some inherent messiness. So if voltage wasn't reliable for force, what do?
They pivoted slightly. Instead of relying just on the voltage, they directly measured the displacement of the actuator.
How far it actually moved.
Exactly. How much the comb fingers moved, which directly corresponds to how much the free end of the fracture specimen was being pulled or displaced.
And how did they measure that tiny movement?
Very carefully. Using optical microscopy combined with video analysis, they could track the movement frame by frame.
Okay, so they had the displacement at the point of fracture. Now what?
Now comes the computational part. They used a powerful technique called finite element analysis, or FEA.
Computer modeling.
Right. They used a specific program called FranC2D, which is designed for fracture mechanics. They built a detailed virtual model of their actual device, including its precise geometry, even accounting for any slight undercutting that happens during the etching and release process.
So a digital twin of the experiment.
Essentially, yes. And using this model, they could input the measured displacement at fracture and calculate the forces and stresses within the specimen right at the crack tip. This allowed them to determine the critical stress intensity factor, KIC, the fracture toughness based on that measured movement rather than the less reliable voltage.
That's a really smart workaround. Using the displacement measurement fed into the FEA model. Okay, so after all that incredibly careful work, the on-chip design, the sharp cracks, the annealing, the displacement measurement, the FEA, what did they find? What's the number?
The headline number, the median fracture toughness value they obtained, was 1.1 MPa square root meter, MPa M sup, 12 sup.
1.1. How does that compare to previous work?
Well, they noted it's generally lower than the values reported in those earlier studies that use the micromachined notches.
Ah, so those less sharp notches might have artificially inflated the toughness values.
That's the implication, yes. Interestingly, though, this 1.1 value is actually quite close to the fracture toughness values that have been reported for single crystal silicon.
Okay, that's interesting. But you said median value. Does that mean there was some spread in the results?
Oh, yes. That's a really crucial part of their findings. The results weren't perfectly consistent across all the samples they tested. There was significant variability, a noticeable spread in the fracture toughness values they measured.
How much variability are we talking?
They quantified it using something called the Weibull modulus. It's a statistical parameter used a lot in fracture mechanics. A high Weibull modulus means the strength is very consistent, very predictable. A low value means there's a lot of scatter.
And their value was?
Low. They reported a Weibull modulus, HAB of 1.9.
1.9, that sounds quite low.
It is. It indicates a relatively wide distribution of fracture strengths. For designers using this material, it means you can't just rely on the average value. You have to account for the possibility that some parts might be significantly weaker. It points to a lower level of reliability, statistically speaking.
Right, that variability is critical for design.
Yeah.
Did they have ideas about what was causing this spread in the data?
They explored a few potential reasons in the paper. One idea relates to the microstructure of polysilicon itself.
The grains.
Yeah, polysilicon is made of many tiny crystal grains. Even though the average grain size was small in their films, the exact orientation of the few grains right at the very tip of that sharp crack could influence how easily the crack starts to grow. Different orientations might present easier or harder paths for fracture.
Makes sense. Little differences at the micro level having bigger effects.
Yeah.
Any other factors?
They also noted that the crack didn't always propagate in a perfectly straight line.
Yeah.
There were sometimes small variations in the crack path direction. And they also speculated about that high-temperature annealing step, the 1,000-degree C bake.
The one needed to remove stress.
Exactly. While essential, they suggested it might have subtly different effects on the very tip of the crack depending on the local grain structure right there, maybe causing a tiny amount of crack tip blunting due to atomic rearrangements, like dislocation emission. And the extent of this blunting could vary from sample to sample.
So the cure might also introduce some slight variability itself.
Potentially, yeah. But it's interesting, despite this range of possibilities causing the scatter, when they looked at the actual fracture surfaces under the SEM after the tests,
Yeah.
they all looked remarkably similar. There wasn't some obvious difference in the appearance of the broken surface that correlated with whether the measured toughness was high or low within their range. The morphology was quite consistent.
Huh. So the underlying reason for the variability isn't immediately obvious just by looking at the break. It's more subtle.
Seems that way. It's likely a combination of those microstructural factors at the crack tip.
Okay, so it feels like they answered the main question about the toughness value, but the variability opens up new questions. Are they continuing this research?
They actually mentioned some ongoing work right at the end of the paper, which sounds really promising.
Oh, what are they trying now?
They're investigating a simplified fabrication process. It uses just one photolithography mask, which is a big simplification in microfabrication.
How does it work?
The idea is to create a larger indent, but not directly in the polysilicon. They make the indent in the underlying oxide layer before depositing the polysilicon.
Okay.
Then, when the polysilicon is deposited over this indented oxide and subsequently released, the topography underneath causes sharp cracks to form directly in the polysilicon layer itself without needing the Vickers indentation directly on the poly.
Ah, clever. And the big advantage.
The big advantage is that this new method apparently avoids the need for that high temperature 1000 degrees C annealing step altogether.
Oh, interesting. So it potentially removes that source of variability we just discussed.
Exactly, and preliminary results sound good.
What are they seeing?
They report an average fracture toughness of 1.2 about 0.2 M sub 12 sub using this new one mask method.
So 1.2, very close to the previous 1.1 median. But what about the variability?
That's the key improvement. They note a significant reduction in the scatter of the data compared to the results from the indented and annealed samples. The plus or minus big 2 suggests much tighter grouping.
So less scatter, more consistency.
Precisely. It suggests this newer, simpler method might be the way forward to get a more accurate and reliable value for the fundamental fracture toughness of polysilicon used in MEMS.
Okay, let's try and wrap this up then. If you had to boil it down, what's the main takeaway from this deep dive into breaking tiny things?
I think the core insight is how this team managed to measure something incredibly difficult, fracture toughness at the microscale, using this really innovative on-chip testing platform.
Right, moving the test onto the chip itself.
Yeah, creating those super sharp cracks, dealing with the processing stresses, and cleverly using displacement and FEA to get the numbers. Their initial result gave us that median value of 1.1 MPa M sub 12 sub, which is valuable. But perhaps just as importantly, they uncovered significant variability in the material's strength at this scale.
That low Weibull modulus.
Right, and that finding spurred them to develop this potentially even better, more consistent testing method. It really highlights that for MEMS design, you can't just know the average property. Understanding the variability is absolutely crucial for reliability.
And why should someone, say, not directly involved in MEMS fabrication, care about this?
Yeah.
What's the bigger picture?
Well, these tiny MEMS devices are everywhere now and becoming more common. They're in your phone's accelerometer and microphone, in medical diagnostic tools, in automotive sensors, tiny mirrors for optical switching,
All sorts of places.
all sorts. And their long-term performance, their reliability, hinges directly on the mechanical integrity of materials like polysilicon. So research like this that gives us a more accurate picture of how these materials behave under stress at these tiny scales is fundamental to making all those technologies more robust, more dependable, and enabling future innovations.
It really does make you think, doesn't it? As we push engineering smaller and smaller, this deep understanding of how materials behave differently at the micro and even nanoscale becomes paramount.
Absolutely.
It leads to a final thought, maybe. Beyond fracture toughness, what other material properties, maybe ones we don't worry about much at the macro scale, suddenly become critical design considerations when you're working down at these dimensions? It feels like a whole new frontier for material science.
It really is. Things like surface forces, adhesion, even quantum effects start to play a much bigger role. It's definitely an exciting area to watch.